What'd you say, Dan? We don't have enough information. What other information would we need in order to be able to even begin investigating and evaluating this idea? Yes, ma'am?
I would probably want to know, like, the proportion of women to men in this company.
Proportion of women to men, total number of males versus females, absolutely. Because for all we know, there's 90 of each. And if that's the case, half and half. That doesn't sound like gender discrimination to me. All right, so go ahead and write down the additional information that you would need, and then I will tell you what that proportion is. So we need to know how many males and how many females there are at the company. All right, so I happen to have that number. There are 60 females and 120 males. So what proportion of the population, what proportion of the employees are the females? 1/3. And so the males would be 2/3. Thoughts about this woman's claim? Could be. Maybe it is, maybe it's not. Is it plausible? I don't know. What could we do to investigate whether or not this was plausible? Yes, ma'am.
I would, first of all, I would check what type of lottery system they use. If it was like random number, or if they use names. And then design a simulation that uses numbers only, so there's no chance for gender bias.
Okay, so let's talk about how we could design a simulation that used numbers. I like that. Because I think we can use that to still try to weed out whether or not this is biased. We can assume that it's not biased and then evaluate that claim. So if we used a random number generator, and this is just one possibility. I want to talk about several possibilities because then you guys are going to perform a single simulation so that all together we're going to end up with, I think, 16 or 17 simulations that we can then plot on a dot plot. So random number generator. Since we don't have people's names, I can't like alphabetize them and then assign them a number. So how could we maybe assign them numbers knowing that there's 60 females and 120 males? 1 through 60 is female. And so then 61 through what would be male? 180. Because we'd have to go all the way to the total number of employees. There would be 120, but we're starting at 61. So 180 would be male. And then how would you actually do this simulation then? You're going to take 10, yes. So you would need to use your random number generator 10 times. And you'd look, does this number fall between 1 and 60? Or does it fall between 61 and 180? We're only going to record the proportion of females because it's the female that has a complaint here. And we're going to look at how many out of those 10 were female. All right, so what's something else we could do? If you didn't want to use a random number generator, how else could we maybe do a simulation? We know it's 1/3 females and 2/3 male. How else could I maybe use something that makes use of those proportions? We could do a spinner, right? Like we did yesterday. How many sections would we need on the spinner? Do I need 180 sections on the spinner? I need 3. Spinner with 3 sections. And tell me how those sections would be divided. 1 is female, and 2 and 3 are male. Do you guys agree that that has the same proportion as the population of the employees at this company? Okay. So we could do a spinner. We could do a random number generator. Any other thoughts? We could roll a 6-sided die. So what would female be then? We could do 1 and 2 for female. And then 3 through 6 would be male. That still has the same 1/3, 2/3 ratio. Okay. You would mention names in a hat. If we had everybody's names, we could do names in a hat as well. We don't have everybody's names. I'm sure we could keep going, but I think this gives us a good start. So I want you guys to pick one of these methods. If you need a dice, I have several die that you can use. If you want to use that method, I'll go ahead and pull those out. Random number generator or spinner, you can use a Google spinner or just type into Google random number generator. So here's what I want you guys to do. You're going to select 10 because they were firing 10 people. And I want you to repeat the trial twice. So every person is going to come and put 2 dots up on the board. All right? You're going to do it twice. Yep. So your paper says once, but we don't have very many people in here, so we're going to do this twice so that we can get enough dots to really analyze this. So take a couple minutes and perform your simulation twice. Then, once you have performed that simulation twice, I want you to come up and put a dot on the dot plot. Or put 2 dots up on the dot plot, my apologies. So you want the proportion that come up female. If anybody wants dice, I've got a whole little container of dice right here. I think I'm going to do mine with dice. Did you have two? Okay, you put both of them up there? Yeah, you can just go. Yep, that's fine. So when I did my two, I got a p hat of 0.3. That was my p hat 1. And then I had a p hat 2 of 0.4. So that's where my dots went. Yours were different, obviously. I want you guys, and you're welcome to work in partners. You might need to look at what we recorded yesterday as well, but I want to know what percentage of the dots represent half or more females being laid off. Just for context, there are 34 dots up here. So I want half or more, and then I want you to try to interpret that percentage in context. So I want you guys to, again, find the percentage after you've copied our dot plot. And using what we did yesterday, I want you to try to interpret that in context.
So are we assuming that this is the proportion of males to females? Is this what we assume?
So this is the proportion of the population that is female.
Okay.
And that's the proportion of the population that is male. Does that help?
So I'm trying to figure out, I can figure out the rest, but I'm trying to figure out the assuming part.
Got it. Got it. Well, let's talk about that. Let's go back here, because I've got a little bit more room to write on the side. And let's see if I have room next to the dot plot. Yep. What was our assumption? That would be our null hypothesis, or HO. What was our assumption? That the company what? We're assuming that they're discriminating? We're assuming that they're not discriminating. That's why we did this random assignment. And we just pulled a lottery, because they claimed that they just pulled a lottery for this, right? We're trying to determine whether or not that lottery was unfair. But our assumption at the beginning, we're going to give them the benefit of the doubt, and we're going to assume that the lottery was fair. Sorry, I'm not going to write the word assume. That comes with it being a hypothesis. Lottery was fair. Specifically, that would mean our p-value would be 0.333 repeating, right? That the proportion of, the true proportion of women is 1/3. And we want to determine how likely is it, knowing that the true proportion is 1/3 and this lottery was fair, how likely is it that half of the people picked to be fired would actually be women? So what would be my alternative hypothesis then? The lottery wasn't fair. Specifically, that it tended to pick who? So we're going with that our p-value is greater than 0.3 in the lottery. Lottery was unfair. That p was greater than 0.333 repeating. This simulation, all these dots, are with the assumption that the lottery was fair. You guys agree that you had a random chance of getting a male or a female with the method that was selected? All right. And it should have been skewed more towards males rather than females, right? Where is our biggest bump of data? Yeah, from like 20 to 40, right? So centering right around 1/3. Does that make sense if we made that assumption? Yeah. And this was an unbiased random simulation. So what was the proportion that were female, or sorry, the percentage of dots that were half or more females being laid off? Yeah. So we're cutting it off here and going over. Why did we pick 0.5? Half the females got fired. So that is this company's result, right? And in total, we have how many dots over there? 7. So we have 7 out of 34, which when you pop that into your calculator, I got 0.2066, right? When I round it. So 20.6, 21 right in there. I'm going to call it 20.6% just to be a little bit more precise. But if you did 21%, that's fine. So about 20.6%. So interpreting that in context, what were we assuming? Yeah, we're assuming that the company is not discriminating. We're assuming that this lottery system was fair. Assuming the lottery was fair. There is a what percent chance? 20.6% chance of getting a sample proportion of female that is 0.50 or greater. Purely by chance. So now that we've done our simulation and we've calculated the percentage of times that this could happen just by chance, do you think that we have convincing evidence that the company was discriminating? Why not? It's above 5%. So this happens a lot more than 5% of the time just by chance alone, just by random luck here. So I would say no. Because 20.6% is greater than 5%. We do not have convincing evidence of gender discrimination. Does that mean that we have no evidence of gender discrimination? No, there's still some, it's just not convincing. You would say, well, if this was totally fair, there should have been more males than females fired because there's more males than females at the company. But purely by chance in a lottery-based system, this occurs often enough that we don't have convincing evidence. Okay, a couple things that I want to point out here. Names that we call some of these pieces. This 20.6%, we call this our p-value. And we'll talk later on about formulas for p-values in situations where we can't run simulations. Assuming that the lottery was fair, that is our null hypothesis. So we assumed that our null hypothesis was true. There was a p-value chance of getting a sample proportion of female that was 50% or greater purely by chance. Down here, when we talked about evidence of gender discrimination, we have our p-value as being greater than, this is called our alpha level. And we'll talk more about alpha levels later, but that 5% that we keep comparing it to, that is called an alpha level. Usually we just say alpha. Gender discrimination was our alternative hypothesis. When the p-value is greater than our alpha level, that means we do not have convincing evidence for our alternative hypothesis. And so we would say that we fail to reject our null hypothesis. One thing I want to make really, really clear is that when we do these significance tests, we never accept a hypothesis. We don't have enough evidence to say this is definitely true. We can reject a hypothesis, or we can fail to reject that hypothesis. That is not the same thing as accepting it. So we either reject or we fail to reject. Does that make sense? All right. Let's go ahead and flip this over on the back and we'll talk about our big ideas. I'm going to have to be writing this down the same time as you guys because I couldn't do it yesterday. So hypotheses. We have our null hypothesis. And we're going to use either a p-value or mu. Sorry, those look like they ran together. Our null hypothesis is either going to be p or mu is equal to our null value. In this case, our proportion was 0.33333. We'll talk later when we get to means about when our null hypothesis is a mean value. For right now, our null hypothesis is our p-value is equal to a proportion. And then we have our alternative hypothesis. That is HA. And in our alternative hypothesis, we are going to claim that either P or mu is less than, greater than, or not equal to whatever that null value was. So the null hypothesis is always p-value equals this, or mu equals this. The alternative hypothesis, we're either going to hypothesize that it's bigger than our null, smaller than our null, or just not equal to. Right. Interpreting our p-value. We're always going to start it with assuming, and then we're going to write this out, whatever our null hypothesis is, assuming our null hypothesis is true, there is a whatever our p-value is, probability of getting whatever the observed result was. Or more extreme, purely by chance. Give myself a little bit more room here. There we go. So interpreting our p-value, assuming the null hypothesis is true, and we have to write out what that is. There is a blank % probability or chance of getting the observed result or more extreme purely by chance. Last thing would be our conclusion. because the p-value is greater than or less than alpha, we either do or do not have convincing evidence for our alternative hypothesis. If the p-value is less than alpha, so less than 5%, we will reject our null hypothesis. If the p-value is greater than our alpha level, then we will fail to reject our null hypothesis. So if our p-value is greater than alpha, then we would say we do have convincing evidence for our alternative hypothesis. Or sorry, we do not have convincing evidence. If p-value is less than my alpha level, then we have convincing evidence for the alternative hypothesis. If the p-value is greater than alpha, then we do not have convincing evidence for the alternative hypothesis. I feel like that language there feels a little bit tricky, but again, we've been talking about comparing to this 5% the whole time. If my p-value, if that percentage is more than 5%, we don't have convincing evidence. If it is less than 5%, then it is sufficiently rare, and we would say we do have convincing evidence. Does that make sense? All right. Go ahead and give the check your understanding a try. Absolutely. There's a green pass right there. You can take that. Yep. probably aren't done with this yet, but let's go ahead and start talking through some of these pieces so that hopefully I'm able to clarify anywhere you're confused. We probably won't get done before the bell. We'll finish it up first thing tomorrow. So I want to state the appropriate hypotheses for performing a significance test. We need to define our parameters. So what would the null hypothesis be? Yes, so I would say P, the proportion, is equal to 0.84. 84% of teens think highly of their mother. What would our alternative hypothesis be? Well, what was found in the observation? In the observation, we found that 135 out of 150 think highly of their mother. So our p hat, 135 over 150, what is that as a decimal? 0.90. If the true proportion is 84, does that strike you as maybe a little high? Maybe. I mean, I'm not exactly sure until a test is performed, right? So assuming that it's less than 84%, when I have an observed value that's above that, would seem a little off to me. We're going to assume that it's actually higher because that was our observation. Or sorry, not assume. We're going to hypothesize. So we're going to hypothesize that P is actually greater than 0.84. P in this case would be the true proportion of teens that think highly of their mother. You're welcome. All right, we'll finish this up tomorrow, and then we'll work on our next activity. Just as a reminder, 9.1 homework is due tomorrow, and tomorrow in class I will pass out the 9.2 homework that will be due on Friday when I get that to you guys. All right?